Hello everyone. In this video we are going to look at kinetics of rigid bodies in 2D or planar, and we are going to use the principle of impulse and momentum to solve this impact problem between two rigid bodies. So here we have the car A, which is moving at 5 kilometers an hour to the right, and it does not pay full attention and drives right into a parking car B and hits it at point P. So here point P and the corresponding point P here, that is going to be the point of contact where the collision happens. And the coordinate of this point, or the offset of this point from the centroid of both objects, are given, as you can see using these four numbers. So the car B is stationary, car A is moving 5 kilometers, they hit, and initially car A does not have any rotation, car B has no velocity or no rotation. The masses of the car are also given, and E is given, as well as the moments of inertia of car A and car B about their centroids are also given. What you need to find are the angular velocities and the linear velocities at the centroid for each one of these objects, okay? So basically, if I go ahead and call these centroids, let's say here, if I call the centroid of car A C, and I call the centroid of car B G. So what we really need is V of C prime, correct? And VG prime. So if you remember, I told you in previous videos that prime means, for us, for my notation, means after impact, without prime means before impact, correct? Right? And before impact, we have the numbers. So before impact, V of C is clearly so many units in the I direction, so it's 5 kilometers. If I divide it by 3.6, I can get it into meters per second, which is going to be 1.39. And it is in the I direction. Right? If you use x to the right as the problem says and y upward, right? You can see y is upward, and definitely x is going to be to the right and z is out of the board toward that. Okay, what about v of g? Well, since g is stationary before the impact, or the whole car B is, so v of g is going to be 0, correct? Before impact. So these are the linear velocities at the centroids, but we also have omegas, right? Omega of both blocks was 0, so omega A and omega B, they were both 0 before impact. What we need is, what are these omegas after impact? Okay, so how can we solve this problem? So clearly when the impact is happening, right? When the impact is happening, the force is exchanged along the x-axis, right? X-axis is the line of impact, and y and z are forming the plane of contact. So the force is exchanged along the x direction. Therefore, the velocities along the x direction will change, but the velocities along the y direction will stay the same, right? But when we say velocity, we have to talk about what we mean by velocity, right? Because here, when we talk about velocity, you know, different points on the rigid body, they have different values for linear velocity. So when I say the velocities are staying the same, what do I exactly mean? Do I mean the velocity at the centroid is gonna stay the same along the y direction and the x will change, or no? velocity of the contact point P, right? So that's the distinction, because when there are two particles, there is only one point that has one single linear velocity. But when you have rigid body, there are different velocities for different points. So which velocity do we consider for the conservation of total momentum and for the definition of coefficient of restitution? So when we talk about the conservation of momentum, since we are using one point to represent the whole rigid body and to show one point that you can basically squeeze in all of the momentum at that point has to be the centroid. So when we write our equation of conservation of momentum, and we say that m of object A times v of object A, correct, in the x prime direction, in the x direction, correct, plus mb times v of b in the x direction. When we say A and B, what point on A and B? As I said, the only way you can show the total momentum of a rigid body at one point is to concentrate it at the centroid. And you know that the momentum of a rigid body is equal to its mass times the velocity of it at the centroid, right? That's the definition you have for total momentum of a rigid body. Therefore, here, when we say about A and B, we better replace them with what? With actually point C and point G. So this is point C, this is point G. This is equal to whatever total momentum of the system is along the x direction after impact. So it's going to be MA V prime of C along the x direction plus MB V prime of G in the x direction, right? This is conservation of total momentum of the system along the x direction. That's one, right? Then in the y direction, we say that what? We say that the components are not going to change, right? Now, before the impact, there was no y component, correct? So VC in the y direction was 0, and that is going to stay as V prime of C in the y direction. And similarly, VC in the VG in the y direction is the same as V prime G in the y direction, because none of the car has any component along the y axis before impact. So after impact, that's going to stay the same, right? Because along y there is no force exchange, so no velocity is going to change. So all we have when we talk about velocities of the centroids here are only x component. The y's are already 0. Good. Now, what do I know about these numbers? So MA and MB are given 1260 and 2700. Okay. V of GX is 0. You can see that here. V of CX is 1.39. And the prime components are both unknown. Right, so you have one unknown here, one unknown there, and definitely with one equation that you have here, if you call it equation 1, you cannot solve for two unknowns, right? It's not going to happen. Okay, so the other equation that you need is the definition of E. E is negative of relative velocity along x after impact to relative velocity along x before impact, right? So what would you write? Would you write as V prime CX minus V prime GX divided by VCX minus VGX? The answer is no. Unlike the conservation of the total momentum along x that you use the centroid velocities, for E, you have to use what? You have to use velocity of the contact point. So what you need here is, if I use 2 points on each one of these objects. So on car B, I call it P of B. On car A, I call it P of A. They are going to be on the top of each other at the time of collision, but they are right now separate points that are on each car. So when you write it, you have to write E as what? You have to write E as here. V prime of PB along X minus V prime of PA along X divided by the very same thing but without prime. So V of PB in the X direction minus V of PA in the X direction, okay? So please keep this important distinction in mind. For E, we use the relative velocity between contact points. For momentum, conservation of momentum, we use the velocities at the centroid. That's a big difference. So E I have, E is given to me. It says it's 0.5, good. But what are the velocities of the contact points before and after impact? Well, PA, which belongs to A, before impact, the whole car was moving with that 1.39. It was in pure translation. Remember, there is no omega. So the velocity of any point on this car, because it's in pure translation, is going to be the same as 1.39. So VPA before impact is positive 1.39. And since car B is stationary before impact, therefore the number for car B, it is going to be 0. The question is, what are these two other things, V prime PA and V prime PB, right? These are two extra unknowns. So although I added one equation in the hope that I can solve for both of these VC prime and VG prime X, the matter of fact, it added two more unknowns. So now I have two equations, but 4 unknowns. Okay, so it's not solvable yet. Then you might say, well, can I find the velocities at PB and PA based on the velocity at the centroids and based on the omegas? And the answer is yes, you have to. So what you need to say is to say V prime at PA is equal to V prime at C plus omega prime A cross R of PA with respect to C, correct? The relative velocity formula between 2 points on a rigid body. Good. So what is V prime C? Well, it has an X component, which I don't know. The Y component is 0. So all it is V prime CX in the I direction, right? So all this one is V prime C along X in the I direction. Omega prime A, I don't know, but it has to be either positive K or negative K. It's a planar problem. So here I assume the magnitude of it is omega prime A and it is in the K direction. It could turn out to be negative K. That's okay. And what is R of PA with respect to C? For that, I need to look at this picture. So it is this vector. It connects C to PA, right? This is R of PA with respect to C. What is it? Well, for that, you need to go 1.7 in the I and negative 0.6 in the J, right? So 1.7 I minus 0.6 J. Right? And now, if you expand it, carry out the cross product and expand it, you will get what? You get a K cross J, which is basically negative I, but there is another negative, so it's positive I. So you will get V prime of CX plus 0.6 omega prime A, the whole thing times I. and then k cross I is j, so it's going to be plus 1.7 omega prime a in the j direction. Right? So this is v prime of PA. And what I need here in equation 2 is the x component of it. So all I need is this guy. This is that x component that I need. Right? So you can write it based on VC prime x, which is an already existing unknown, and omega prime a, which is another unknown. Okay? So this guy here can go into equation 2 and replace it. Also, you can write a similar formula for v prime pb based on v prime of g, because pb and g belongs to object b, and then omega prime of b cross r of pb with respect to g. And again, if you replace v prime g has what? An x component that you don't know, a y component that is 0, so this one is going to be v prime g in the x direction I. Your omega b prime you don't know, you just assume it's positive k, it could be negative k, that's okay. And r of pb with respect to g, again, if you go back to your picture, it is basically this vector. Right, this is r of pb with respect to g, which is negative 3.2i plus 0.6j, correct? So let's write it down. Negative 3.2i plus 0.6j. And again, if you carry out the cross product, you will get k cross j, which is negative I, so you will get v prime gx, and then minus 0.6 omega prime b, this whole thing times I, and then k cross I is j, but there is a negative, so it's negative 3.2 omega prime b j. And again, here, if you look, the component that you need here is the x component of PB, which is this guy here. So this one is going to go there, right? So now if you plug in these two into equation 2, your equation 2 looks a little bit better. It's going to be E equals negative of, if you replace it, it is going to be v prime of gx minus 0.6 omega prime b, and then minus v prime cx plus 0.6 omega prime a, divided by 0 minus 1.39, and this e itself, if you want to replace it, it is going to be 0.5. So now your equation, if you call it equation 3, this 3 looks a lot better. So now you have 1 and 3, you have 2 equations, but still 4 unknowns. V prime cx, V prime gx, as well as the 2 omegas. Right? So still 1 and 3 gives you 2 equations, 4 unknowns, so you need 2 more equations. Where do they come from? So if you look, equation 1 is conservation of linear momentum. But when you have rigid bodies like this, you can write equations about angular momentum. What about angular momentum? Well, if you know from your dynamics lectures, some of the moments about a point, if you integrate it versus time, correct, and integrate that, this in general, depending on what kind of point is point O, this can be written as, if O is a fixed point, it can be written as angular momentum about point O in position 2 minus angular momentum about O in position 1, and this goes from T1 to T2, correct? This is called the principle of angular impulse and the change in angular momentum. This point O has to be either a fixed point on the rigid body to write it this way, or it has to be the centroid to write it like that. Okay? In general, when this point O is not any of these 2 points, a fixed point on the rigid body or the centroid on the rigid body, the relation is not as simple. So for point P, the contact point, can I write such a thing? Well, not exactly, right? Because I cannot say sum of the moments about point P is equal to time derivative of h about point P, okay? This simple relation that I could write for a fixed point or centroid of a rigid body is not necessarily always valid for what? For any arbitrary moving point P. So what can I write here? Well, here I need to show you a little bit of change in the equation, and then we'll see whether we can do anything about point P. And you might wonder, why should we write everything about point P? Why do we insist at writing these impulse momentum equation for angular motion to write it about point P? The reason is when the two blocks, the two cars hit each other, the force is exchanged at point P. So if you take the moment in any of these objects about point P, the left term is going to be 0 because the collision force passes through point P, so it has no moment about P. And mg and n, since this is the top view, they are going to be in the board or out of the board. And basically, since they are equal, mg and n, total of the moment of those two forces with respect to P is also 0. So there will be what? No total moment in any of the object with respect to point P. So whatever the right-hand side is, it's equal to 0. And if we write it one time for object A, one time for object B, that gives us the two extra equations that we need here. Okay, so it's very good if we can write something about that the impulse, the angular impulse about P is equal to something, because that angular impulse is 0. Now, what can we write? Well, here we can start from the summation of moments about the centroid is equal to dH about the centroid over dt, correct? We know this is applicable. Now I'm gonna do a change in moment. Summation of moment about C can be written as summation of moment about P, correct? And then minus, if you move your forces from C to P, correct? So this is your rigid body. This is P, this is C. And this is some of the forces that you can show on point, let's say point A, for example. This is where some of the forces is applied. So here, some of the moment about C is going to be this vector, whatever this vector is, R of A with respect to C. If I call this point A, it's going to be this R of A with respect to C cross summation of the forces. That's some of the moment about C. What about some of the moment about P? That is going to be what? That is going to be this vector, which is R of A with respect to P cross some of the forces. And clearly, I can write this R of A with respect to P as R of what? This R, which is R of C with respect to P. If I add this R of C with respect to P, this vector in orange, if I add that to R of A with respect to P, correct? Or sorry, R of A with respect to C, that gives me R of A with respect to P. So instead of this vector, I can write it as this one minus that. And when I cross product it, this one cross F is going to be some moment about P. The other term would remain. So it is going to be R of C with respect to P cross summation F. Right? This is called the change in moment. This is called the change in the moment. So instead of some of the moments about C, I wrote it this way, right? This is called shift in the moment. And in one of my videos, if you go and look under the dynamics playlist, you can see this. Shift in the moment, shift in the angular momentum, shift in the moment of inertia, and so on. So this is how I change it from point C to point P. Good. What about H about C? It's a similar thing, okay? So I can write it as d over dt of H about P is H about C plus, if you squeeze all of the velocity in point C, and then cross multiply R of C with respect to P times that. So H of C can be written as H of P minus R of C with respect to P cross MV. Right? And which V? V at the centroid. So it is going to be M times V at the centroid. Okay, this is called the change in angular momentum, the shift in angular momentum. Okay, now what can we do? So here, summation of the forces, as you know, this is equal to m times acceleration at point C, right? And the question is, what is the time derivative on the right-hand side? So it is going to be dhp over dt. And then here I have a product of two terms that could be variable. So it's the time derivative of first one cross the second one. So it is going to be minus d of R of C with respect to P over dt cross MVC. And then plus R of C with respect to P cross M, derivative of AC is AC. Right? So this is equal to summation of moment P minus R of C with respect to P cross MAC. And if you look here, there is a common term, one that is here and one that is here, so you can get rid of them. The question is, what is d of R of C with respect to P over time? That's a vector attached, or it's a part of the rigid body, and the rigid body is rotating with omega. So based on what we know, it is omega of the rigid body cross this vector. Okay, that's the derivative of any vector attached to a rigid body is omega cross the vector. And now the question is, what is this whole thing here? Right? So if you know from a rigid body, V of point C can be written as V of point P plus omega of the rigid body cross R of C with respect to P. And if you look, this guy here is the second term. So instead of the second term, I can write it as what? If I take Vp to the left side, I can write it as Vc minus Vp. That's what I can write that as. Correct? That term is Vc minus Vp. It's the relative velocity between C and P, or V of C with respect to P. Good? So if I clean this up, now that you know what it is equal to, and continue, I will get summation of the moment about P is equal to dH with respect to P over dt, then minus what? This term cross this term. And what is that? Or sorry, this term, my bad, this term cross this term, right? Vc minus Vp cross MVC. Well, clearly VC cross VC is 0. These two negatives would cancel, so you'll get your final equation to be some moment about P is equal to dH with respect to P over dt plus m Vp cross Vc. So you should write it like this. You see there is an extra term here. Now, in the case of this example, if I focus on object A or object B, what's Vp cross Vc for object A? Well, for object A, it is moving straight like this. So V of P and V of C are both the same 1.39i. Since they are collinear, this term is 0. So I can write it like that, exceptionally. There is no initial rotation. If it has some rotation before hitting, then the velocity of these 2 points will not be collinear. This term will not be 0. But right now it is. Okay, so for object A, that was pure translation, I can write it. What about object B? For object B, it's completely stationary, right? So point G and point P, both of them are stationary. So both of these terms are 0, so the cross product is again 0. So for both of these objects, I can simply write it like this. That sum of the moment about the contact point is dH over dP of d of HP over dt. And the good thing is, for both of the objects, as I told you earlier, there is no total moment about P. The total moment about P is 0. So when this guy is 0, it means that HP in position 1, which is before impact, is going to be HP in position 2, which is after impact. So you can say that the angular momentum for each object about the contact point is going to stay the same before and after impact. They are going to be the same number. So there is a ton of discussion here before you can show that, yes, the total angular momentum for each object about the contact point is 0, okay? There are special cases here where the second term just vanishes, okay? Now with all that, let's go back and use this one time for object A, one time for object B, and try to get the 2 extra equations that we need. Good, so now we write that the total angular momentum about point PA before impact is the same as the angular momentum about PA after impact for object A. And what is the angular momentum about the contact point? That's the same as angular momentum about the centroid plus R of C with respect to the contact point cross MV. And here this means MVC. Okay, the shift in angular momentum. So this thing is the same as H prime C, the same quantity, but after impact. And then R of C with respect to PA, which is the same vector, and cross MAV prime C. Okay. And what is H about C? If you remember from my dynamics lectures, H about C, it can be written as I about C times what? Times omega. So this is what you can write. And this one too, you can write it as I of A actually. You don't write it as I of C, but you can write it as I of C. That's okay. Let me write it as I of C, it's better. I about C times omega prime A. R of C with respect to P, we had it, if you remember. In both cases, R of the contact point with respect to that. So if you see here, that's P with respect to C. We need C with respect to P, so it's negative of this vector, negative 1.7 I, 0.6 J. The same thing about this vector. V of C is, we know, we have it. It was 1.39i. V prime C, we don't have it, but we know it has an X component only, and it is in the I direction, right? Because the J component was 0. And here, every entity is going to be about the K axis, right? The omegas are about K, and when you carry out the cross product, I cross I is 0, J cross I is going to be negative K, so everything is K or negative K. So when you simplify it, you will get simply a scalar equation. And that is going to be I about C times omega A. And then here you have J cross I, as I said, is negative. So you're going to get negative 0.6 times M of A, which if you want to plug in the number, or let me just keep it as is, times 1.39. This is equal to IC omega A prime, and then here again you have a negative K, so it's negative 0.6 MA times V prime CX, right? And the I's are given, both of the I's are given in this problem. If we go back and look at the I's are 24 and 7600. Correct, so I have the I numbers. This is 2400, this is 7600, or no, sorry, both of them are 2400. 76 is for block B. MA was also given. If we had MA somewhere, it is 1260. So if you look at this equation, what is this? And omega A, omega is the initial rotation, which we did not have any initial rotation, so that's simply 0. So if you look at this, that gives you an equation between two of the unknowns, which are omega prime of A and V prime of C, right? This is a useful equation. It gives me an equation without introducing any new unknown. So I have equation 1 and 3. This one I would call equation 4. That is a very useful equation. And then I repeat the very same equation, but this time for block B. So for B also I say H prime PB and HPB are the same, right? The total angular momentum of block B about the contact point is going to stay the same. And again, this is going to be HG plus R of that G with respect to PB cross MB VG. This is going to be equal to H prime G, then plus R of G with respect to PB cross MB V prime G. Okay, and again, H about G, as you know, it is I about G times omega. And MB was, you look at the number 27 and I is 76. So 27 and 76. And this I, as I said, is 7600. Block B has no rotation before impact, so this is 0. Omega prime B is an unknown. V of G before impact is entirely 0. V of G after impact is only the X prime component, because the Y prime component is simply 0. And R of G with respect to PB, if we go and look at it, it's the negative of this guy. So 3.2i minus 0.6j. So this guy here and this guy here are 3.2i minus 0.6j. Right? So if we carry out the cross product, again, everything is going to be k component and or negative k. So here, this whole thing is 0 on the left-hand side. And on the right-hand side, I have 7600 omega prime b. And then here you only have j cross I, which is negative k. There is another negative, so that's positive. So it's going to be plus 0.6 times 2700 times v prime of gx. And this guy I can call equation 5. So now I have 4 good equations. Equation number 5, equation number 4, equation number 3, and equation number 1. I have 4 unknowns and 4 equations, and they are all linear equations. So if you use equations 1 and 3 and 4 and 5, I have already solved it. You will get v prime of c is the same as v prime cx in the I direction, and v prime cx, I found it. It is 0.147, so it's going to be 0.147 v prime of g is only the x component of it, and that guy is 0.567 I. The units are meters per second. Then I found omega prime of a, which is in the k direction, but it's negative, so negative 383 radians per second. And negative means it is going to rotate clockwise. And finally, omega b prime is going to be negative 0.12, 0 radians per second, which means that guy is also going to be clockwise. So if you look, see if it makes any sense. So what does it mean? If you look, the velocity of car A, the centroid of car A, this guy before impact was 1.39. Now it is reduced to 0.17. So the car that hits the smaller car would slow down, of course. This car was stationary, it was 0. Now it gets a speed of 0.56 or 0.57. So it is being kicked forward. And of course, that's correct. And it says both of the cars start to go clockwise, start to rotate clockwise. Does that make sense? If we take a look here, so this is the situation with the cars. There is this force coming from car A to car B, and there is the opposite of that from car B to car A. So this is like F of B on A. This is F of A on B. And clearly, if you look at the centroids, the moment of each one of these forces about the centroid is definitely what? Clockwise, as you can see. So both of the objects will go clockwise, right? So this car is going to go like this, and slow down. The big car is also going to go a little bit like this, and goes from stationary to some non-zero value. Right, so it goes like this. And this one also goes like that, but slower and rotates. Good, so this is what's going to happen when you hit it like that. Now, if the position of the contact point was different, so if you hit it here on the bottom right, then the direction of rotations will be counterclockwise. And if you hit it right behind the centroid, then there will be no rotation. Okay, so the direction that they rotate and how much the speed are going to reduce or increase depends on E, depending on where you hit, what are the masses, what are the eyes, and how fast each one is moving. So this is a rather complicated problem, but I hope it was useful to you. And this way you can analyze what's going to happen when two cars as rigid bodies have a collision. Thank you so much. I will see you in my next problem.